All right, so let's take a look. In this problem, we are talking about the traffic flow rate, so cars per hour, across an intersection is R of t, which is equal to 200 plus 900t, blah, blah, blah. Okay, where t is measured in hours. So I think it's always good to kind of imagine, what are we talking about? We are talking about, we're putting in t, we're getting out r. T is measured in hours, or in the hour, okay? Where R is in cars per hours. So this would be cars per hours, okay? And t equals 0 is 6 a.m. That's very important. So if I sub in 0, that really means 6 o'clock in the morning, okay? How many cars pass through the intersection between 6 a.m. and 7 a.m.? Okay, so here we go. Let's see. If they want to know the number of cars that pass through the intersection, how many cars? Not cars per hour, but the actual number of cars. Okay, how am I going to take my function that is measuring cars per hour and turn it into cars? Well, hopefully we recognize whatever that curve may look like. If we find the area under the curve, the area under it, that would be calculated. In calculus, we do it as length times width, but of course we do it with like millions of little rectangles, or we use antiderivatives in the fundamental thermocalculus. But the idea is still the same. It's area, and it's length times width. So therefore, our length being measured in hours, I'll spell this out, R, HR, our length times our width, which would be cars per hour. Now notice those units would divide, leaving us with cars. So just by drawing this kind of reinforces the idea that we absolutely want to integrate this function. It will give us the right units. So we're going to do the antiderivative of 200 plus 900t minus 180t squared. And then remember, the integral means summation. It means add up. So what we're doing is we're adding up all the cars that are passing through, cars per hour. How many pass in the first hour, second hour, third hour? Add them all up. That gives us our total number of cars. Now, what do we integrate from? Well, we're starting at 6 a.m. So if we're starting at 6 a.m., remember, we wouldn't sub in 6 for t, right? We'd be subbing in 0. T of equals 0 is 6 a.m. All right, so we're going to sub in, I just got done saying that. I put a 6. We're going to sub in 0. That's 6 a.m. And then we want to end at 7 a.m. So what would be the number up here? Well, if 6 a.m. is 0, then 7 a.m. would be 1 hour after 6, so we'll do 0 to 1. And that right there is our setup, right? And a point I always like to make is make sure these numbers that you're putting in your bounds make sense to sub in for t. They should have those units, because after we do the antiderivative, we're going to take those and sub them in. So what does 1 represent? Oh, 1 hour after 6 a.m. What does 0 represent? 6 a.m. It's an hour. It's a time of day. Okay, so we're good. All right, so let's do the antiderivative of this. The antiderivative of 200 would be 200t. The antiderivative of 900t to the first would be t squared divided by 2 minus 180t cubed divided by 3, evaluated from 0 to 1. Okay, and of course we could do a little bit of simplification as we go here. I'm going to do both at the same time. So we're going to do 200 times 1, as we sub in for t, plus 900 divided by 2 would be 450 times 1 squared, minus 180 divided by 3. Well, let's see, 3 times 6 is 18, so that'd be 60. There we go. 60 times 1 cubed. Now, the fundamental thermocalculus says you sub in the 1, minus. Now we do the exact same thing, subbing in the 0. Now, this is going to be far less interesting because it's going to be 200 times 0 plus 450 times 0 squared minus 60 times 0 cubed. And for those of you who have been paying attention, that just makes 0, right? Doesn't do it every time. Don't just make that assumption, but in this case it does. So therefore, 200 plus 450 minus 60. So let's see. This would be 200. That'd be 650. Take away 60. So that'd be 590 cars. Okay. So I hope that helps, and I hope it helps you evaluate future problems that are similar.